Dapeng from Cambridge talking about CHERI stuff. Go for it.
Good afternoon, everyone. My name is Dapeng, second-year PhD student at Cambridge with Professor Robert Watson. And today I'm going to share my early-stage research on library-based software compartmentalization on CHERI. So first off, what is CHERI? It is shorthand for Capability Hardware Enhanced RISC Instructions. It is an extension of existing instruction set architectures that comes with a new hardware representation for pointers and also new instructions for manipulating them. So as you can see on this diagram, you have a C pointer to an object, and traditionally the pointer is just an integer address, but with the CHERI architecture, this pointer will have more information, such as the lower bound and upper bound, in which of the memory that you can dereference with this pointer. And it also comes with permission bits, such as load, store, execute, etc., that you can use to limit what you can do with this pointer. Right. So what properties can we get from a CHERI system? First of all, capabilities are unforgeable. It means you cannot just create these pointers or capabilities out of thin air. You can only receive them from somewhere else. The second important property is that capabilities are monotonic, meaning that you cannot increase the privilege of capabilities that you have, but only reduce them. So the implication is that arbitrary memory access is now forbidden. You have to possess the right capability to access any memory that you want to access. So what is the stage of research with CHERI at the moment? Our group at Cambridge, with collaborators, have been working on this for more than 10 years now. We have successfully extended the RISC-V and AArch64 architectures with CHERI. We have formal properties, formal specifications written, and formal proofs of the security properties that we desire, including monotonicity and others. We have real server-class CPU fabricated with ARM. It's called Morello, high-performance quad-core computer. We have the FreeBSD operating system fully ported to run with capability pointers. And we also have thousands of packages ported to run on this new architecture, including a usable desktop environment. So this is all about CHERI. And now I'm going to move on to compartmentalization. So let us motivate the need for compartmentalization through an example. Suppose that there is this pure computation function that is applied by some untrusted third-party library that you want to use in your application. It has this signature, takes a buffer, a size, returns an integer. So this function is supposed to have no side effects, but how do we guarantee that when you are a consumer of this library? Well, you might say capabilities are unforgeable, and we have permission bits. So suppose we just set this capability to buffer as a read-only capability and pass it to this function. Then this function will only be able to read the buffer. It won't be able to write or corrupt it otherwise. So it cannot possibly have any other side effects. Well, this is wrong, because abstractly, the programmer merely sees pure computation, accepting a read-only capability to this buffer. The concrete implementation of C implicitly confers many more powerful capabilities to the untrusted function. These include the stack pointer, the return address pointer, program counter, and unused argument registers and callee saved registers, the global function and data symbols such as system calls that this function might invoke. So it's not really secure, and we want to be able to limit the power of this untrusted function to only those that they necessarily need to carry out what we want it to do, which is the essence of compartmentalization. Now, there are many existing solutions that rely on memory management unit or language level isolation. For example, we may split a program into multiple processes and use IPC to communicate with each other to ensure isolation, or we can use language level techniques such as WebAssembly. But they tend to have some costs in terms of performance, compatibility, or human effort. And my conjecture is that with the CHERI architecture, we can achieve the sweet spot of all of these three things at the same time. Let us analyze the problem that we face. So again, we want untrusted code to gain only the capabilities that they necessarily need, which raises two questions. First, how do we demarcate the trust domains? How do we actually draw the lines between the compartments? Question two, how do we limit the privileges granted to each trust domain? What is the mechanism for doing that? Let us now look at the first question. And I propose to use dynamic libraries as the unit of isolation. We treat each dynamic library used by the program as a separate compartment. And the threat model we have is that the L files containing the untrusted libraries are assumed to be well-formed, and their metadata are assumed to follow appropriate security standards. These, you might question, are these really a realistic threat model? And I would argue that these are actually reasonable assumptions, because even though you do not trust this library, developers mostly just compile them by source themselves. So if you trust the compiler you use, you can reasonably assume that the L files generated are well-formed and follow appropriate security standards. But I wonder if we can do better. Can CHERI actually defend against even maliciously crafted L files as an attack vector? Can you just run any arbitrarily obtained binary ELFs and still reach a certain level of security guarantee? Okay, so this is the first question, how to demarcate boundaries. The second question is, what mechanism do we use to limit the privileges? And I propose to use the runtime linker as the trusted computing base for setting up this whole compartmentalization regime. First, my work is done on the Morello computer with the CHERI ISA implemented. And Morello has this new feature. Essentially, it has two modes of user space code called executive mode and restricted mode. So in these two modes, the stack pointer, the thread pointer, and some other registers are banked across the two modes, meaning that there are two sets of these registers, one for each mode. So when you switch the mode, you get a different stack pointer, thread pointer, etc. And another feature is that code running in executive mode will be able to read and write restricted mode registers, but not vice versa. This is a very useful feature for our purposes, because we can just run the runtime linker in executive mode and all other application code in restricted mode. Now, function calls that cross library boundaries between your application code will be intercepted by a trampoline that is generated by the runtime linker. This trampoline also runs in executive mode. So we have this trusted intermediary that will enforce certain security policies that we desire when we transition from one compartment to another. Similarly, when the function returns from the called compartment to the calling compartment, the trampoline will be re-entered and will reverse all of those changes that it has made. As you can see from this diagram, you have library A, library B on the right, and if you call a function in library B from library A, you will first actually enter the trampoline, which updates the register file and sets up, enforces some security policies, and when you return, the trampoline will be entered again and it will reverse these operations. So now we have this mechanism for enforcing security policies. Now we need to actually add some policies. So I've implemented several policies, and I will discuss two of them here. So one of them is called stack switching. So suppose functions foo and bar belong to different shared libraries, and they share the same execution stack. We have a problem, because if we execute foo and then we execute bar, then at the moment foo returns, it may leave valid capabilities above the top of the stack. Now, when we enter bar again, bar will be able to access these leaked capabilities from foo, and thus gain unauthorized privilege. So my solution to this is to simply switch the stack used by foo and bar within the trampoline. So we allocate a dedicated stack per library, and the trampoline will switch the stack when it is invoked. Another feature which I also implemented is well-bracketed control flow. So you have, when you return from a function, you always return to where you are called from. You cannot return anywhere else. Okay, so towards the end of my, this is the last slide. I would like to discuss some of the next steps that I wish to do. First is, how do we tell the story of compartmentalization for C++? What does compartmentalization even mean for C++ programs? Specifically, what properties do we desire, and what are actually achievable with a reasonable performance overhead? The next question is, what is the best way to specify security policies? Can it just be a set of symbols that each library can or cannot link against? Lastly, can we really get this sort of automatic push-button security? Can we just run any software in compartmentalization mode and get better security? Probably not, due to this thing called compartment interface vulnerabilities, which I have cited in my paper. Basically, you can just break software and leak information by supplying maliciously crafted arguments through its API. So the interesting question then is, what is the minimum intervention needed to vastly improve security by mitigating these compartment interface vulnerabilities? For example, can we just split libraries into I/O parts and computation parts and gain more security? These are all questions that I would be happy to discuss with you. Thank you very much.